Chapter 19, Part 1, Electric Charges, Forces, and Fields. So let's talk about atoms first. So they contains protons, neutrons, and electrons. Protons and neutrons have roughly the same mass, about 1.67 times 10 to the negative 27 kilograms, so it's very, very small. And electrons have a negligible mass compared to the protons and neutrons. They're about 10,000 times less. So about 9.11 times 10 to the negative 31. Protons are positively charged. So what we have is we have a positive charge for protons, and electrons are negatively charged, but even though their masses are different, their charged are the same. So you have the amount of charge for proton and neutron and electrons, they are the same. And neutrons are neutral. They don't have any charge associated with them. The electric charge. So the symbol is E, the unit is Coulomb or C. It represents only the magnitude of electric charge, not the sign. So positive or negative, you have to put it there. This 1.6 times 10 to the negative 19 coulombs. This is something that electron has it with negative and proton has it with positive. And charge is quantized, so only integer multiple of E exist because we have an integer number of electrons, okay? For example, you do not have 2.3 electron. It just doesn't exist. You have 1 electron, 2 electrons, 3, 4, and so on and so forth. And changing the magnitude by adding or removing electrons. For example, in general, we use Q or capital Q to signify the charged. So Q would be the number of electrons or protons time the electric charge of either proton or neutron. For example, if you have, let's say that if you have 12 electrons, okay, Q, the total amount of electric charge would be 12 times 1.6 times 10 to the negative 19. And we know since these are electrons, we have to have a negative here. So we put a negative sign. That means my overall number, whatever it is, will have a negative value associated with it. So I have 12 times 1.6 times 10 to the power of negative 19. Okay. Separating charge. So all objects are inherently neutral. They do not have positive or negative, okay, unless we do something to give them some sort of a charge, okay, either positive or negative. Electric charge can be transferred between objects. Typically, electrons are transferred, okay. Protons do not move, so positive charge or protons will stay. So P or positive charge, okay, doesn't move. This is a fact because atoms are fixed in their position. Electrons can move from one atom to the other, so they can, they can be considered as the moving charge. The protons will remain at their position. So what is the net charge if an object gains electrons? So it's gaining negative, so the total charge would be negative. And if it's losing electrons, it's losing its negative. Thus it will have a positive charge overall. So this would be positive and this would be negative. Charge is conserved. In other words, it cannot be created nor destroyed. It can only transfer from one object to the other, but the total amount of charge in the entire universe will be the same. Let's take a look at this question. Complete the following statement. When a glass rod is rubbed with a silk cloth, the rod becomes positively charged. So we have a rod, okay, that has a positive charge inside right now. Okay, that means its electrons are gone. okay? That means negative charge are transferred from the rod to the silk. Negative charge are transferred from the silk to the rod. Positive charge are created. No, that's absolutely incorrect. Positive charge are transferred. Positive charge do not move. Protons won't move. Protons are atoms. A nucleus, they are fixed inside the material. They won't move. However, electrons can move. So negative charge are transferred from rod to the silk. That would be your correct answer. Let's take a look at this one. So electric charge, what we have is when a amber rod is rubbed with fer, some of the electrons on the atoms of a fer are transferred to the amber. If we were to do the same with an identical rod, what would happen if we push the rod towards each other? So in other words, what you have here is that you have a positive, negative, positive, negative, positive, negative electrons and protons, and this is neutral in general. Once you're rubbing this rod with this cloth, okay, these negative charge will go and trapped inside this rod, and it's going to left a negative rod for us and a positive cloth for us here. So if you have a negative object here and a negative object here, they will repel, okay? They will repel. They will have a force because two negative charge will repel, two positive charge will repel. What we know is that if you have a positive and a positive, so positive and positive will repel, negative and negative will repel. However, positive and negative will attract. So what we have here is this. These two will repel. These two will repel. But these two will attract. Okay, it's the same. We have two negatively charged rod, and then what's happening is that they will have a opposite force. They'll repel. Conductors. So why does a metal spoon placed in the boiling water heat up? Electrons move faster, so they're creating heat, and heat travels from one end of the spoon to the other because charge or electrons move through the object, okay? Conductors, these are the materials that allows electrons to flow easily, like a metal, like aluminum, for example, or copper or gold. And so good electrical conductors tends to be a good thermal conductor as well. Okay, so if you have a good electrical conductor, you have a good thermal conductor as well. In other words, if it's a good electrically conductor object, it will transfer heat easily for us. Insulators, these are materials that conduct electricity very poorly, okay? So like plastic, wood, rubber. Most good thermal insulators are good electrical insulators as well. So for example, that's why we've used to cover the metal wires to keep it charged in the wire, because we don't want the charge to be somewhere. You know, you want to keep it in a safe place. And then let's talk about this, and then we'll go back to another subject. So metals are on the left-hand side of the periodic table, okay? And because they have few valence electrons, metals have tendency to lose electrons. So this is very important, okay? Some valence electrons becomes detached from atom to migrate through the materials. So one electron will move from one atom to the other, and it will move from second one to the third one, from third one to fourth one, and so forth, okay? When one end of the conductor is placed in contact with the charged object, the roaming electrons move in the conductor. If the object is negatively charged, for example, the electrons move away from the charged object. I'll show you some examples later on. What will happen now? Let's go to this question. What will happen if an electron, if the object is positively charged? What will happen to the electrons if the object is positively charged? So if something is positively charged, it means it has a less amount of electrons inside it. So the electrons are gone. They have been transferred to another object. So we have charging by contact. Charge can be transferred between objects. For example, a negative charge rod will transfer electrons to a metal sphere on contact. Okay. When the rod is removed, the excess electrons will remain on the sphere. Okay, we'll talk about it later on. Because like charge repel each other, the negative charge is evenly distributed around a metal sphere. We'll talk about it again. So these two, I'll talk about them again in an example. What occurs if a rod is positively charged? Think about it. You have a negatively charged there, but what would happen if the charge was positive? It will attract electrons, okay? I'll talk about that one more time later on. So let's take a look at this. Charging without contact. So what will happen if we bring a negatively charged rod close to a neutral metal sphere? So I have a negatively charged rod here. So there are excess amount of electrons inside this rod. And then this is a conductor. This is a conducting sphere. It means that the electrons can move easily. So what happened is that the electrons in this rod will repel the electrons in one side of this metal sphere. So these electrons will be pushed over there, okay? So you have these electrons right there. In other words, what's going to happen is that you will have all of these positives on one side and all of these negatives in the other, because these electrons are repelling the electrons of the sphere, and they will go all the way to the maximum that they can go, okay, which is the other side of the sphere in this case, because electrons and electrons are repelling. Remember, protons are fixed. Protons, or the positive charge, is the atom, and it will be fixed inside the object. The electrons are gone. These electrons have moved all the way to the other side of the sphere because they can move, and electrons are repelling one another. The charge in the sphere is persuaded to separate. Can you think of why? As I said, they will all go to the other side. If you remove the rod, the charge will return to the random orientation. So as soon as you are removing this, all of these charges will go back to their natural position, okay? So, charging by induction. Suppose the sphere is, in the previous example, has a grounding wire, a wire that connected to the ground. And what would happen when a charged rod is brought near the sphere? So what we have is that we have a sphere here, for example, okay? That's our sphere. And then we have a rod. Now let's say that this is our rod, negative rod. And now what we have here is that we have a connection to the ground, which we usually show it like this, okay? And then I have a negative charge inside this rod. This rod is negatively charged, okay? So rather than all of these electrons to come over here, what's going to happen is that they will all of these electrons will go to the ground, okay? So I am left with a positively charged sphere because almost all of these electrons will go to the ground. So let's read this. So the charge will separate, but now some of that charge is transferred between ground and the sphere. If the grounding wire is removed at this point, okay, at this point, if I remove the grounding wire, then if you pull the rod away, then there will be a net charge in the sphere left. Okay, so if you're looking at this, I have a negative charge here and a distribution of positive charge right here because all of the electrons or the freely moving electrons are going to the ground. Once you remove the ground connection and you remove the rod, you are left with a positively charged sphere because it lost all of its electrons. They transfer to ground, they're gone. So that's what it does. So all of these electrons are going to the ground. Once you remove the ground and the rod, you're left with a positively charged sphere. Okay, so let's take a look at this question. An initially electrically neutral conducting sphere is placed on an isolated stand. In other words, not connected to the ground. A negatively charged glass rod is brought near but does not touch the sphere, okay, without moving the rod. So we're keeping the rod in its position. A wire is then attached to the sphere that connects it to the earth ground. Okay, so now you have a wire connecting the sphere to the ground. The rod and the wire are then removed simultaneously at the same time. What's the final charge on the sphere? Okay, think about it. It's negative, positive, neutral, 50% positive, 50% negative. What do you think? So it's exactly the same question that we had before. Yet you're bringing a negatively charged rod to a sphere, okay, that's neutral, okay, everything is evenly distributed, okay. Once you bring this close and you connect this sphere to the ground, all of these electrons will go to the ground, so you are left with a positively charged sphere at the end, okay. So this will be positive. Induction and insulators. So recall, the insulators do not allow charge to flow easily in the materials, like wood. It doesn't, like plastic, it doesn't do anything, right? When a charge rod is brought near a neutral insulating sphere, the charge does not move to the opposite side because it just can't, okay? Opposite charge moves slightly toward the rod, like a charge moves slightly away. So what I have here is this. Let's say that I have two spheres, okay? Two spheres. One is conductor, the other one is not, okay? So I have a conductor here. And the other one is insulators, an insulator sphere, all right? Now what I have is I am bringing a negatively charged rod close, okay? I am bringing a negatively charged rod close to one another. What's happening is that all of the positive will remain and all of these negative ones will go all the way to the other side when it's a conductor. But if it's not a conductor, the electrons cannot move, okay? They'll just stay at their position. They won't move because they can't move easily from one atom to the other, like wood, okay? But what's happening, they will have some sort of an orientation, okay? So if you consider that this is the atom, it will be the form okay? Positive will come to this side, positive will stay on this side, electrons will go to the others. For example, if this is the positive at the center, electrons will spend more time to the other side. So all of these electrons are moving like that, right? So the possibility that electrons are spending time on the right-hand side is more compared to left-hand side if you are bringing a negatively rod close to it. If this is not a conductor, electrons cannot go from one atom to the other, but they will spend more time on the right-hand side here because you have a negatively charged on the left. They can't go, but they will at least to their maximum, they will go all the way. They will spend more time further away from the negatively charged rod. Okay? But if it wasn't a conductor, they will just go all the way to the other side of the conductor. Semiconductors and photoconductors. So semiconductors have properties in between conductors and insulators. The properties change with chemical composition and temperature. And photoconductors materials become conductors when light shines on them. Electric forces. There is a force between two charged objects. Object with charges of the same sign repel. We know it. Two electrons will repel. Two protons will repel. So we know two positives will repel. And we know two negatives will repel as well. Okay. Objects with charges of a positive sign attracts, and the opposite signs attract. So for example, if you have a proton and an electron, they will attract one another. Okay. So let's take a look at this. Fur with charge Q and rubber rod with charge -2Q. So they will attract. Two protons, we know, they will repel. Two electrons, we know, they'll repel. Like mechanics in physics 1011 or physics 1, these external forces can cause some sort of an acceleration. Do you remember the Newton's second law? You had F of net or F of external, or we showed with sigma F is mass times acceleration. These forces can cause acceleration in the object. So Coulomb's law. Charged objects exert a force on each other, okay? And these forces are proportional to the magnitude of their charge. So the more charge, the more force. And so how will the force between two charges Q differ from the force between two charges 2Q? Okay, so in other words, you have a double of charge here, so you will have more force when you double the amount of charge. The force is inversely proportional to the square of the distance between two charges. Just like the gravitational force. You remember the gravitational force from physics 1? Gravitational force from physics 1 was capital G, m1, m2 over r squared. That was the gravitational force. And so it's the same. This force is inversely proportional to a square distance between the 2-point charge or two charge distributions. So let's take a look at this. How will the force between two charges change if the distance between them triple? So in other words, if I have the force being proportional to 1 over r squared, then this force, if you triple the distance, you have 3r here, so 3r squared, which means that F is proportional to 1 over 3 to the power of 2 is 9, r squared. In other words, compared to before, it is 1 over 9 times bigger. Okay, so it's 9 times smaller. All right, so now you have this new F. As you can see, you have a factor of 1 over 9. All right, so this means that you have 1 over 9 1 over r squared. That was our original relation. Now you have 1 over 9 as a ratio, or 1 over 9 as a coefficient right there. Okay, so Coulomb's law, that's the law. It really looks like the gravitational law, but in our case it is F equals K, Q1, Q2 over R2. K is a constant. It's 8.9 times 10 to the 9, okay? Newtons meters square over C square. And the direction is determined by the sign of the two charges. We talked about it in previous slides. If they're the same, they'll repel. If they are different, they will attract. And so if you're looking at this, we have two positively charged, they will repel. We have one positive, one negative, they will attract. And we have two negatives, they'll repel. And the force between the two charges are action-reactions pair. So they follow the Newton's law. In other words, they are equal. The amount of charge that Q1 is applying to Q2 is the same and equal to the amount of force that Q2 is applying to Q1. Okay, so in other words, the amount of F12 will be equal to amount of F21. All right, their directions are different, but their magnitudes are the same. And these are action reactions. Action reactions. What was the Newton's third law? Remember, there are two forces, one action, the other one is reaction. They have the same magnitude, okay, but they're in the opposite directions, okay? They will not cancel out because you have two objects. If you take one object individually, you have one force acting on it, all right? So they won't cancel out, but they are action-reaction pairs. So let's take a look at this lecture question. Force between two charges and the changing charges. So two objects separated by distance r are each carrying a charge of plus q. So in other words, I have a plus q here, and they are distance from one another is r, like that. And the magnitude of the force exerted on the second object by the first one is F. So you have two forces. Okay, so that's F. That's F. Why they're in this direction? Because we have two positives, so they have to repel. Okay. And then if the first object is removed and replaced with the identical object that carries a charge plus 4q. In other words, you just change the plus q to plus 4q. So we'll have a plus 4q here, same distance. All right. So you'll have a different force. I'm just going to call it F prime. Okay. So I'm just going to call it F prime. And they're, again, action reaction, they're the same. They have the same magnitude. They have the opposite directions. What's the magnitude of electric force on the second object? Okay. So in other words, we know the magnitude of the previous one is F. We want to know what the F prime is. So the F prime is K, Q1, Q2, R squared. K, Q1 is 4Q in this case, or, we have one of them is 4Q. And the other one is Q. And then R squared. So when you're looking at this, you have K, you have 4K. You can just bring this 4 out. 4K, Q, Q, R squared. But this one is our previous force. So this one is just F. So what you're having is that you are having F prime being equal to 4F. Okay? So that's the answer. Let's take a look at this question. Two objects, A with charge positive Q and B with charge positive 4Q, so they will repel, are separated by a distance R. The magnitude of the force exerted on the second object and by the first one is F. So they're applying force F to each other. If the first object is moved to the distance 2r. Okay, so now you are having r, you had r, but now you're going to go away to 2r. Okay, from the second object, what's the magnitude of the electric force on the object? So what we know is that this is F, K, positive Q, positive 4Q over r squared, that's F. But now the F prime is K, positive Q, positive 4Q, but instead of having r squared, you have 2r squared, okay? In other words, you can have this 2 to the power of 2, which is 4, and you can bring that out of this equation. So you will have 1 over 4, because 2 to the power of 2 is 4, 1 over 4, K, Q, 4Q over r squared. And this is our previous relationship. Okay, so we had F prime being 1 over 4 F. Okay, in other words, that's your final answer. Electric forces between two charges. So we have two charges here separated by distance 2a. One of them is positive q, the other one is negative 2q. Find the force on the charge positive q. Okay, so let's first draw it. They are opposite signs. One is positive, the other one is negative. So they will attract. So they will attract one another. Okay. These forces are equal. They are action reactions. They have the equal magnitude. So if you find one, in fact, you have to find the second one because they are the same. So this F is K, Q1, Q2 over R squared. Okay. So K, Q1 is positive Q. Okay. Q2 is negative 2Q. Okay. And R squared is 2A squared. So F is K, 3Q squared, or no, 2Q squared. Where did I get 3? F is K, 2Q squared. And I have 2a to the power of 2 in the denominator, so we'll have 4a squared. Okay, so this 2 and this 4 will cancel. You'll have 1 over 2 k squared over a squared. Or you can write it like that if you want to spend time and write more cleaner. Q over a 2. Okay, so that's the force. Now let's talk about this very important law, Coulomb's law for multiple charges. So if there are multiple point charges, the forces add by superposition law. Okay, in other words, if you have Q1 and Q4 here, they're positive, they'll cancel out, so you have F14 here, and then you have Q1 and Q3, so you have F13 in this direction, and they're all positive, so they'll all repel. And then you have Q2 and Q1, they are both positive, so they repel. On Q1, you have essentially three forces, F14, F13, and F12, coming from all of these three, charged particles. But you have a net force acting. In fact, if you consider all of these charges, they will add up, okay? And the way that we find the sum of them is the law of superposition. Okay, what was it? It was if you have a first force, for example, F14, okay, and then the second force is F13, for example, and then F12 is the third one, then the net force acting is F. Starts from the first, it starts from where the first vector starts, and it will end where the last vector will end, okay? So they start at the same point, they finish at the same point, okay? In other words, if you have, for example, F1, F2, F3, F4, and F5, then your net force is this. Starts from where the first vector is starting, and it will end where the last vector is ending, okay? So in other words, in our case of an example here, the total net charge, the total net force experienced by this Q1 is F1, which is the sum of F14, F13, and F12, okay? So let's take a look at this. So if you have more than two charges, use the law of superposition. The total force on a charge due to multiple charges is equal to the sum of the individual forces due to each separate charge. This law is your friend. I've talked about it many times in Physics 1. Now, here is the useful example that you had for Physics 2. Now, let's take a look at this. So, now find the magnitude and direction of the force on charge positive Q right there, okay? So the distance between plus Q and negative Q is A. So what you have here is, this distance is A, all right? And the distance between positive Q and negative 2Q is 3A, okay? So this distance is 3A. We're looking to find the net charge acting on this. So we know that negative and negative will repel, but we want to talk about this one. We know that negative and positive will attract. So let's take a look at this. You have a charged particle here, positive Q, right? And then here you have a negative Q. Then here you have negative 2Q. Okay, so these will attract. Okay, so this is F. And then these two will also attract because negative and positive will attract. And I'm going to call it F prime because I just wanted to distinguish it from F. They're not the same, so I'm going to show it in a different way. So let's talk about F first. F is K, Q1, Q2, R squared. K, we know what the value for K is, 8.9 times 10 to the 9, okay? K, Q1 is positive Q, Q2 is negative Q, and R squared is just A squared, okay? So you have K, Q squared, A squared. That's what it is. Now let's talk about F prime. F prime is K, Q1, Q2, R squared. K, Q1 is positive Q, and Q2 is negative 2Q, okay? A squared or R squared, the distance between them is 3A, so you have 3A squared. So you have K, 2, Q2, 9A squared. So F prime is 2 over 9 K Q squared A squared. And if you're looking at this, this guy is just F. Okay, this is F. So in other words, your F prime is 2 over 9 times F. All right, so you have two forces in one direction. This gets really interesting. So you have an F in this direction, and you have an F prime in the same direction. So the total force is F plus F prime, or 2/9 F plus F, okay, which is 11/9 times F, which is 11/9 K Q squared A squared, okay? So let's say that they are not lining up in one line, and you have you have them like that. Find a force on the charge positive Q. Remember, force is a vector, so split it into the components. In this case, you don't have to split into the components, but in our next example, you have to. So here you have 2A here, so you have an A here and an A here. That's a distance, okay? And then you have 2A here as well, all right? So you can kind of find this distance, R. So this distance R is 2A squared plus 2A squared under the square root. So distance R is just, let's see, 2 times 4A squared, because they have a power of 2, right? So then you are left with square root of 8 times A. Okay, so that's your R, square root of 8 over times A. And then what you have here is that you have 2-point charges. One is positive Q, the other was negative 2Q, with the distance R, which is square root of A times A between them. So your F is K, Q1, Q2, R squared, which is K. Q1 is positive Q. Q2 is negative 2Q. And R squared. So you have K 2Q squared and R squared. So you are having square root of 8 A to the power of 2. So what you have is K 2Q squared. Square root of 8 to the power of 2 is just 8. And you have A squared here. Okay, so you have 2 over 8, which is 1 over 4. K Q squared A squared. Okay, let's talk about another very important example. Here, I have a challenge for you. So I have another charge. This is literally the same example that we had before when I solved it, but in our case, we have another charge, negative Q here. So you have a R here, and R, as you remember from our last example, is the square root of 8 times A. And then you have another R here. Let's call it R prime. Okay, and R prime is just A. Now let's talk about the direction of these forces. You have a positive and a negative, so they will attract. Let's call this F. And you have a positive and a negative, and they will attract, and let's call this F prime. Okay. So you know how to find F, and you know how to find F prime. So in order to find the net force, all right, you have to add them up. But you can't just add their magnitudes. These are vector products, and they have to you have to add them in a vector way. Okay, so what you have here is this. You have a triangle. All right. This is 3A. This is 2A. And this is 2A. And this is 90 degrees. 90 degrees. That leaves us with 45 degrees here and 45 degrees here. Okay. Because you have this 2A and this is 2A, so you're left with these two. And that means that your F and your F prime will have a 45 degrees angle between them. Okay? And you know how to add them up. So F of net is F squared plus F prime squared plus F squared plus F prime squared plus 2F F prime cosine of 45 degrees. That's the angle between the two forces. That's one way of doing this, okay? The other way of doing this is to split the F into X and Y components, okay? So what I have here is this. I have my X direction here, and I have my Y direction right there, okay? I have my F prime along the Y direction, so let me divide the two methods. So I have my F prime along the Y direction, okay? And then I have my F with an angle of 45 degrees, like right there. So this will have a F sub X, and this will have a F sub Y. So F sub X is F cosine of 45, and F sub Y is F sine of 45 degrees, okay? So then the net force along X direction is just F of X, which is F sine of 45, but then net force along Y direction is F prime plus F sine of 45. And by the way, this is cosine along the X direction. It doesn't matter because it's 45 degrees, sine and cosine are the same. But it's important to be consistent. So this is cosine of 45 degrees. Okay, as I said, sine of 45 degrees and cosine of 45 degrees are the same. If you don't believe me, just subtract them and you'll get 0. Okay, so the net force along the Y direction is that. And now, in order to find the total net force, you will have F of net along the X direction squared plus F of net along the Y direction. So that's F of net along the X, and that's F of net along the Y. So you have two ways. First is to find the angle between the two forces, which in our case was 45, and it was very easy to find, okay? And using this formula to find the net, or F1 plus F2, or F or plus F prime. The second way that you could do it was to, so this is the second way, second method, okay, is to split forces into their components. So I split F to F of X and F of Y. So along the X, I have only F of X, But along the y, I have two forces, F prime and F of y. And I add them up because they're both along y. Once you do that, you have a net force along x and net force along y, and then you can just easily use this formula. So total force in that case is F of net along the x to the power of 2 and F of net along the y to the power of 2. So Coulomb's law, summary, Coulomb's law is stated in terms of point charges, but it is also valid for spherically symmetric charge distribution, as long as the distance is measured from the center of the sphere. For example, if I have a sphere, if I have a perfect sphere, okay, being evenly distributed charged. For example, you have a negative charge evenly distributed in this sphere. You can think that this is a point charge with the same charge. For example, if this is 10Q, negative 10, you know what, let's call it something else, negative 12Q, then you can think that this negative 12Q is centered at the center of this sphere. It'll do this, it'll do the same. It'll be the same object. But rather than having a spherically distribution object, I can think of it as a point charge positioned at the center of the sphere with the same amount of charge. Okay? Or you can think of this ring of negatively charged particles being evenly distributed. We can think of them as that there is a point charge center located at the center of the ring, which is right there. Okay, so you can have, like, for example, if you have negative 5Q, you can think that this negative 5Q is in fact a point charge at the center of this ring, and you can say that I can consider it as a point charge at the center. This is kind of similar to what we had in physics 1 for the center of mass. The center of mass of a sphere is at the center. The center of mass of the ring is at the center. So you can think and looking at it like that as well. So let's talk about this lecture question. Net force. A charged particle is located at the center of uniformly charged halo sphere. Okay. What is the net electrostatic force on the charged particle? Okay. So we have a, let's draw something. So I have a sphere, right? And I have another sphere. And this is halo, so I can later on move this around and have a halo sphere, kind of like that. Okay, and what's happening is that this is charged. So it's, let's say that it's, for example, positive. Okay, so I have a uniformly charged halo sphere, kind of like that. Positive charge or negative charge, doesn't really matter, but it's charged. And then you have another charge at the center, right there. Let's say that this is also positive. Okay, what's happening is this, that this positive and this positive will repel. This positive and this positive will repel. And then if you do the same for every single particle in this sphere, okay, you are left with something like this. You are left with a point charge at the center experiencing a force, a uniformly distributing force like that. So there is no net force acting on this because they will cancel out. Okay, they will cancel out. It will be something like this. You will have, let's say that this is our this is our point, for example, here, right? Let's say that this is our point here. And then, so what you're gonna have is this. You will have a force in this direction, a force in the opposite direction, a force up, a force down, force in this direction, force in this direction. They will cancel out, all right? So they will all cancel out. So no net force will act on this object. So the net electrostatic force on the particle will be 0 newtons because all the charges in the sphere are either repel or attract to the particle, so they exert no force on it. So A is correct. So that's the end of part 1 of the chapter 19 of this chapter. End of part 1. We'll continue with part 2 right after this.